Ben? Yeah, thanks for inviting me, or thanks for asking me last minute to fill in, same as last year. So long as this conference keeps being disorganized, I'll have a job for life, so very happy about that. This is based on some joint work in progress with Vivek Shende. Work in progress, and it's very much work in progress, so feel free to attack me if there's something you don't like. I can try and defend myself, which I will do. So the title is pretty explicit. I'll probably spend the first half of my talk explaining a generalization of my previous work with Vivek that as a result produces a mirror symmetry equivalence at the large volume limit point. So part one of my talk is going to be mirror symmetry at large volume. And then in part two of my talk, I'll explain some ways that you can really juice this up in order to produce a mirror symmetry equivalence, in order to deform this mirror symmetry equivalence to get a mirror symmetry equivalence between two smooth Calabi-Yau varieties. Deforming this. So let me start by recalling that on the B side, what happens is what we start with, so I'll be sort of enhancing this sort of starting data more and more as I need it. And at bare minimum, we want to start with some variety which I'll call Y0, and let's assume it's a normal crossings variety. Of course, in the Gross-Siebert program, I think we've moved on to more general things than just normal crossings. We can have toroidal crossings, but let me stick to this simple case. What I want to do with it is I want this to come from a polytope. Let me say, for the moment, I'm going to want a topological manifold, which I'll call B, with a polyhedral decomposition. So this expresses B as a union of polytopes. So an example is going to be B could be the circle, and I write it as the union of three intervals, or n intervals. Or I could take B to be a tetrahedron with, for instance, the natural decomposition into four triangles. Or I could take a finer polyhedral decomposition. What I want of this topological manifold is that Pi are the moment polytopes of components of Y0. Right, so I want this to be a normal crossings variety whose components are toric varieties. Or toric varieties, and they're meeting along toric subvarieties. So in this case, when I had B as the circle with some number of points, what that's going to tell me is that Y0 is, well, okay, there's not that many one-dimensional toric varieties. Y is going to be a union of P1s. If I took B to be this tetrahedron, then Y0 would be the toric boundary of P3. Okay? Right, local, just to sort of put this on the board for later in the talk, the local model of a singularity, so maybe I can say that I can sort of restrict to small sort of neighborhoods down on this base. Those gives me some neighborhoods of y0. So I'll say y0 has étale charts. I'll call them y0u, where u is like a neighborhood of something downstairs, that are equivalent to something of the form z1 dot 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 zk is equal to 0 times maybe nothing is happening in the other variables. So I have c star to the, and if I want my y0 to be, I want it to be n-dimensional or n-1 dimensional. Let's say it's n-dimensional, so this is going to be n plus k, n minus k plus 1. So these are some local charts which I'm going to try and deform later on. And a reminder is that z1 dot dot zk equals 0. This inside of c to the n, c to the k, this variety here is a mirror to the k minus 1 dimensional pair of pants. K minus 1 dimensional pair of pants. So let's explain what that is now. So, the pants I usually call P something, but I'll just call it pants. So, pants K minus 1 has two definitions. One of them is it's a variety cut out by the equation 1 plus x1 plus dot 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 plus xk equals 0 inside of c star to the k. And the other definition is that this variety is equal to c star to the k minus 1 minus a pair of pants 1 dimension lower. Pants k minus 2. Okay. So what am I going to do with these basic building blocks here? What I'm going to do is what I want to do first of all is to build a mirror to y0. So goal is to build a mirror to the space y0. And basically what I'm going to do is I'm going to say, okay, y0 is built out of some configuration that looks like this. So therefore, my space is also going to be built out of some configuration of pairs of pants, and it's going to correspond also to the same combinatorics of this base B. So the first step is this. So let me remind you of this earlier work, which I did with Vivek. So reminder, let delta be the Newton polytope of a Laurent polynomial f from c star to the n to c. So for instance, delta is equal to the standard simplex, say, in R2. In that case, and I'm going to require that delta contains 0. what we showed, all right, I'm going to reinterpret our theorem. Okay, well, first of all, maybe I should say what it is, although I don't want to get into too many technical details. Let me just say that given such a Newton polytope, we get a tropical curve, right, that's dual to that Newton polytope. And our theorem was that f equals 0, I'll just say it this way, has a Lagrangian skeleton whose pieces correspond to, so if I think of this polytope delta, so think of delta as part of a fan of cones, right? So I told you that delta contains 0, so here's 0. And to think of this as a fan of cones, I pretend that this edge is a ray going this way, this edge is a ray going this way, and the interior of the polytope is a two-dimensional cone. So in that case, f equals 0 has a Lagrangian skeleton whose pieces correspond to the cones in this fan. So I need to say what a Lagrangian skeleton is, and I need to say how those pieces correspond to the cones in this fan. Roughly speaking, a k-dimensional cone, a k codimension cone, so k codimensional cone. So for instance, this cone, this ray here is codimension 1 inside of R2, gives a k torus times r to the n minus 1 minus k. So let me say what this is in this example. So I've got my 3 cones here. And so this one gives me a circle. This one gives me a circle. And this one gives me a 0 torus times r, which interpolates between the 2 circles. And so this green thing you should think of as a pair of pants. And you can see that this Lagrangian I've drawn sits inside the pair of pants. So what are the nice things about this Lagrangian skeleton?
Do you want to put the origin in the interior? Because
Sorry?
now we see 2 rays if you do like this, and so 2 circles, but the pair of pants has 3.
Well,
so I think
I drew the pair of pants here. Here's the pair of pants in green. Everyone can see the green, right? Yeah. And then I drew a Lagrangian inside of the pair of pants, which is this thing. It's got the 2 circles and the edge connecting them. Mm-hmm. And my claim is this is a Lagrangian skeleton of the pair of pants.
I see.
Do you want to give a name to this theorem?
So to this theorem?
Yes.
Oh yeah. So well, the topological version of this theorem, topologically, this was due to Rudot, Sibylla, Truman, Zaslow, and then to prove that this thing is actually a Lagrangian inside of here, symplectic version of this theorem was due to myself and Vivek Shende. So what is a Lagrangian skeleton? Okay, well I've given talks about this in the past. I don't want to spend my whole talk talking about the Lagrangian skeleton. I'll say 2 nice properties of it. 2 nice properties. of Lagrangian skeleton. So one is this allows you to compute the Fukaya category. So the Fukaya category of a symplectic manifold. If a symplectic manifold has a Lagrangian skeleton, that means it's a Stein or Weinstein manifold. Symplectic, in fact, Weinstein manifold localizes along its Lagrangian skeleton. So that's one thing. And the second thing is that Lagrangian skeleton, one way to think about what a Lagrangian skeleton is it encodes some kind of gluing of symplectic manifolds. Lagrangian skeleton encode gluings of Weinstein manifolds. So technically I should say that Lagrangian skeleton encode gluings of Weinstein sectors or Weinstein pairs, which means a Weinstein manifold together with something along the boundary that you're gluing along. So just in this picture, what I should imagine from this skeleton is that, sorry, I know most people can't see the bottom of the board. I got mad when everyone wrote on the bottom of the board, but I'm doing it now. What I should imagine is that each of these circles is the skeleton of some cylinder, and then each of these rays coming out of the circle is specifying me some piece at the contact boundary of that cylinder that I want to glue along. So when I glue these two manifolds along, I extend a piece out like this, and then I can see that these two cylinders connected by this bridge are a pair of pins. Here's the hole right here. Okay. So now let me reformulate that theorem. So I'm going to reformulate that theorem by using a little trick. So notice a hypersurface H in C star to the K is the complement. Let me do this backwards. I want to say something about complements of hypersurfaces. The complement of a hypersurface in C star to the K, C star to the K minus 1, is a hypersurface in C star to the K. So that's a fact. And it's Newton polytope. So let me call this hypersurface H. So its Newton polytope is the union of, so I take the Newton polytope of H, which is in R to the K minus 1. I multiply it by 1, so that gives me some polytope in R to the K. And then I take the union with 0, and I take the convex hull of that thing. So for instance, if my Newton polytope, if H was a one-dimensional pair of pins, then I take the Newton polytope of H, which was the standard simplex in R2, I put it at height 1 in R3, and then I add 0, and then I take the convex hull. So I fill that thing back up to a full dimensional polytope. And I can see that this thing is equal to the Newton polytope corresponding to a two-dimensional pair of pins. So that's very nice. So why did I do this? So now let me explain a corollary of that theorem. And the corollary is that so let C star to the n, whatever, C star to the k minus 1, I should have made it k. C star to the k minus 1 minus a hypersurface H has a skeleton which lives over the polyhedral decomposition dual to the tropicalization of H. So what do I mean by that? Example, let's continue with this example of H as a one-dimensional pair of pants. So its tropicalization looks like this. So trop H is a polyhedral decomposition of R2. And it has a dual decomposition with dual decomposition that looks like this. And then maybe there should be some things at the boundary. Let me not worry about that. But the point is the dual polyhedral decomposition will have one vertex for each two-face, one edge for each face, and so on. The claim is that if you work this out, then this C star squared minus H has a skeleton which has two torus above each vertex and one cylinder above each edge, and then a two-cell above this. Somehow it's the same thing as here, where a codimension, maybe I'll say this, I'll write it here so everyone can see, above a codimension K face, a codimension, I'll use another letter, codimension R face, we have an R torus. Right, so if I sort of were to try and draw this thing, I would get kind of torus, 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 some cylinders, and then this, which is in fact the skeleton of a two-dimensional pair of pants. So now I can say what the mirror to a general large complex structure limit is. Which is obtained by Weinstein gluing. So the new generalization of my theorem with Vivek, so this is a theorem, so Vivek. Oh yeah, so I should have said that already we used this Lagrangian skeleton to prove a mirror symmetry statement, and the generalization of that mirror symmetry statement is here. So given BP as before, so B, remember, is a topological manifold, and P is a polyhedral decomposition, I guess with fan structure at the vertices. B equals union of polyhedra Pi as before. There exists a Weinstein manifold X, X0, such that X0 has a skeleton corresponding to the dual polyhedral decomposition of this. So let me call that P check, the dual polyhedral decomposition, as before. And the corollary is that the wrapped Fukaya category of X0 is equivalent to the category of coherent sheaves on our initial large complex structure variety Y0. So maybe I sort of go back to the one-dimensional case again and explain what this construction of X0 was. So let me do an example first, though. So example, b equals this, as before. Then we saw that y0 was equal to 3p1s, like this. And then x0 was equal to, so I took this, and then as we learned from many previous talks in this conference, the mirror to a node is like I delete something here. So I've got kind of zoop, zoop, and zoop. Sorry, that didn't work out so good. Let me try it again. It's a 3-punctured torus. Cool. So the construction of x0 is that near, so take some neighborhood in this topological manifold B, and let me assume, maybe let me restrict myself to the situation where this polyhedral decomposition always locally looks like, its boundary locally looks like tropicalizations of pairs of pants. So if I restrict myself to that case, such that the polyhedral decomposition intersected with U looks like the tropicalization of a k minus 2-dimensional pair of pants, and then over U, let x0u, this is going to be one piece in this x0, be c star to the k minus 1 minus this k minus 2-dimensional pair of pants. Of course, I didn't have to let this be a pair of pants. I could have let it be any tropicalization of a hypersurface, and I could do this, but for simplicity, let me restrict myself to this case. Then this x0u is then x0u is mirror to this piece y0u, which lives over u on the b side, and then you use your knowledge. So we have this Lagrangian skeleton of this x0u. We know everything about it, and we can use our knowledge of the Weinstein structure to glue these together. So use Weinstein structure to glue x0u globally to u. So that's what the construction of x looks like. What we hope, so let me say one conjecture about that, and then I'll give maybe one more example, and then I can move to part 2 of my talk.
Can I ask, are you
Yes.
that you can prove the homological combinations of all what is opera?
Well, but only for, I mean, this is only at the large complex structure limit. So this y0 is always like the boundary. It's something along the lines of like the boundary of a toric variety. It's not like a smooth hypersurface in a toric variety yet.
And also a question, like for the left-hand side, by the ratified category, do you literally mean the ratified category or like the micro-shift category?
Well, they're equivalent by a theorem of Ganatra, Pardon, Shende.
But I thought they only proved that for like the partially racked version. Probably.
They're, well, okay, they proved various things in various cases. Let me say that their theorem does apply in this case.
Okay.
Yes. Somehow this skeleton we're using is a particularly nice skeleton for a number of reasons. And one nice feature is that like all the full properties of the Ganatra, Pardon, Shende, at least what they've done so far, allow us to conclude this is in fact the wrapped Fukaya category in this case.
So maybe it's a basic question about Gross-Siebert program, but this central, this toric gluing, does it need to be pure dimensional usually? Or,
well,
in your case it is.
In my case, I'm restricting to this situation where I have a
right. In particular, all parts are the same dimension.
Yes.
Yeah.
Yes.
Does it need to be general?
You can ask Bernd about the full generality of the Gross-Siebert program.
Pure dimensional.
Yeah.
And you can't allow singularities.
What?
On B, right?
On B. I haven't gotten there. I'm going to allow singularities on B. That's going to be the whole point of this talk, is allowing singularities in B. But we don't see the singularities in B yet. So at this point, B may have singularities, but I didn't tell you yet that B was an integral affine manifold. I never said, well, I just said those words, but yet I haven't equipped B with an integral affine structure, so you don't know, maybe the integral affine structure will have singularities, but this, in order to get this y0 and x0, I only needed this topological manifold with a polyhedral decomposition and a little bit of extra data, this fan structure near the boundaries of the polyhedra.
Is the reason that B is a topological manifold is because of normal crossings assumption? As opposed to like just some kind of complex.
Well, I don't know.
You said topological manifold.
I don't know.
Okay.
Yeah, so let me, are there any more questions? Okay, maybe what I wanted to say, okay, so let me state a conjecture, which is that x0 has a map to B, which is a Lagrangian torus vibration away from the boundary of the polyhedral decomposition, away from the boundary of the polyhedral decomposition of B. So the idea is that, you know, this, the idea is that y0, of course, has a map down to B that's a Lagrangian torus vibration, log tori, degenerating over the boundary of B. And the mirror to that mirror should be tori with parts disappearing over the boundary of B. Disappearing over the boundary of B. So the example that you should keep in your head is in this example right here, maybe I'll just go over here. So the example is that, you know, so this thing has a map down to this thing here, which is the moment map. And as for this thing, locally, it looks like this. I've got a cylinder minus a point. And so I imagine just if I use the normal sort of, what the moment map this cylinder would have, if this point weren't there, then I would see there's sort of one point where I'm missing a point here. So that's recorded in this thing here. So I can record that there's very recently, within the last couple of weeks, been a paper of Ilya Zharkov, who's here, and Helga Rudat, establishing a version of this map, a version of this in the topological case. So they describe essentially some map here, but without anything about symplectic structures or Lagrangian torus vibrations. So Vivek and I are still working to try and get this map symplectically. If you have any ideas, love to talk to you about that. Right. Okay. So that's the situation at the large complex structure limit, large volume limit. Now, if there aren't any more questions, I'm going to spend the rest of my talk trying to deform away from that point.
No. That's it? This is all we're going to say about this? He's going to move on.
Well,
Okay.
What more do you want me to say?
Well, you said you were going to say something about the integral affine structure.
Yeah, the integral affine structure is all about deforming away from the large volume limit. The point is, at the large volume limit, the integral affine structure isn't visible to you.
You just have a union of corridors. And how you choose to measure an affine structure across the edges is what will give you the singularity in this movement.
So let me...
Should I not think of this as like x0 as something removed from the... Like you have a Donaldson, like a divisor on... But you don't know. But that means that there's...
No. I mean, I haven't... No. I mean, x0, the point is that globally, I had some local pieces, right? So there's something confusing about this. This confused me for a long time. I have some local pieces, and I'm gluing them together, but I don't necessarily know what the total divisor is that I want to glue back in. It'll make sense in a second. I'm going to start explaining right now. So you're free to ask me again in a minute. So we want to deform. So on the, let's say what happens on the B side. So on the B side, we have local charts, which I've already mentioned, of the form z1 dot 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 z to the k is equal to 0. We want to smooth these. So what does this sort of, if you have this chart, how can you smooth it? How can you put it into a family such that the general fiber is smooth? The answer is that it smooths to z1 dot 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 z to the k equals, the simplest case you might say is z1 dot dot z to the k equals t, but more generally, you might have a smoothing of the form z1 dot 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 z to the k equals tf. In this talk, f is going to be of the form f of x equals x1 plus dot 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 plus, maybe I write it this way. It's going to involve some of the other z variables. F of z equals 1 plus zk plus 1 plus dot 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 z to the k plus r. So it's going to be plus. It's going to be very simple. But the point is, the total space of this smoothing has singularities at the 0 locus of f. So the 0 locus of f we're going to see is going to give us precisely those singularities of the integral affine structure. So let me now say something about the B side smoothings. So if y0 had a smooth log structure globally, then it would have a global smoothing with smooth total space. So there would be no singularities of this integral affine structure. So the singularities of this integral affine structure correspond to singularities, the failure of being able to put a global smooth log structure on y0. In fact, this would be unique. So I planned to look up some things before this talk, but I forgot my computer, so I didn't get a chance. So I'll just say I learned some things from, there's a paper of Helge Ruddat with, this is
2D, 1D.
Felton and Philip. Whoops, Ruddat. Felton, Philip, Ruddat. Sorry, I've got those in the wrong order. And I think Chan, Leon, Ma is the other paper that's related to this that has a Bogomolov-Tian-Todorov theorem for singular Calabi-Yaos with log structure. So somehow the idea is that like log structure is precisely the thing that allows you to pick out a unique deformation. And if you had a global smooth log structure, then you would have a global deformation of this z1 dot 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 z to the k, such that on each chart, the restriction of that deformation would be z1 z to the k equals t. But we don't have that in general. So suppose y0 has a smoothing, but a smoothing with singular total space. Singular total space. Total space. This corresponds to some log structure. Log structure with singularities in codimension 2. And this is further going to correspond to some integral affine structure on B with singularities in codimension 2.
So
what do you mean by smoothing with a singular total space?
So
Like a deformation?
the total space of the smoothing is, the total space of the family is some variety itself, and that family may have a singularity. But the individual fibers outside 0 are all smooth. So that's kind of the situation we find ourselves in general. Outside of very special Y0s, we're not going to be able to smooth it with a smooth total space, or else you wouldn't need to do the Gross-Siebert program. We have this discriminant locus. And kind of that's where all the juice is. Okay, so what, so suppose I have this integral affine structure on B with singularities in codimension 2. What is this going to tell me how to glue in on my mirror side? Maybe I should make a little chart here. So let me kind of B side, A side, and then, whoops, I didn't leave enough room for the labels. Let me do it here. So on the B side, what the boundary of my polyhedral decomposition is corresponding to is, the boundary of my polyhedral decomposition is corresponding to the singularities of the smooth fiber. So this is the moment, maybe I'll just call this B, I'll call this BP. So this BP is what you might call a moment X-ray. That's what the terminology Alan Knudsen told me, that it's the moment map with all of its sort of moment subvarieties, with its fixed loci highlighted, of Y0. And on this side, this boundary P, so this is a moment map thing, and this boundary of P is a tropicalization of the deleted divisor. Right, which corresponds, the deleted divisor is corresponding to the singularities of Y0. Now, this discriminant locus, so this is with singularities in codimension 2, so this is going to be codimension 2, this is going to be a discriminant locus, and in fact, it's going to live entirely inside the boundary of this polyhedral decomposition. The idea is that the places in the total space where there are singularities are contained within the sort of, in this integral affine manifold, they're contained within the places where your single central fiber has singularities. So, sorry, this isn't very legible. Someone should have told me to write bigger. It's all your fault.
Can you write bigger?
Thank you. Yeah, so what I wanted to say here is that, so this was about a moment map, and this was about a tropicalization, but then when I get to delta, those two things switch roles. So now delta, like I said, is the failure of the smoothing to be smooth, which is controlled by the 0 locus of F. So delta is precisely the tropicalization, trop, of F equals 0, where F is over there. That's the smoothing thing. This is the smoothing. It's too small. So this is now about tropicalization, and then over here, what's the discriminant locus going to tell me? The discriminant locus looks like a moment X-ray of the singularities of the divisor D that I'm going to glue back in. Okay, so I didn't say what D is, but it's the divisor I'm going to glue back into X0. So I'll give an example of what I mean. That when I see this picture, this tells me on the A side that I should take C star squared and delete a pair of pants. So that's what my X0U is going to be. Let's call this chart U. And now the point is that what do I want to glue back into X0U? So this chart is going to tell me, so this chart tells me glue a pair of pants into x0u. So I get x0u union a one-dimensional pair of pants is going to be my sort of partially compactified thing. So okay, that's not that exciting. So now what if I do the same thing, but now I have a discriminant locus here. So my discriminant locus doesn't have a color at the moment. I'll make it red. So I put a little x here. Now what that's telling me is that what I want to glue back in, so x0u is as before. Right, so my sort of large volume limit doesn't change because I told you that didn't depend on these singularities. But now what this x0u is going to be is it's going to be, what this d is going to be, it's going to be a pair of pants, but now it's got a node in it, right? And this node, like locally near this node, you're seeing the moment map for like the leg of that pair of pants sort of having a node here. So that's what that means. Does that make sense to people? So that's what this little chart is supposed to denote for you. So now I'd like to actually deform.
So this is stupid. You can't have singularities in the interior of the polygons?
No, no. I want my discriminant locus to be like.
So for like, if you look at kind of integral affine structures on a given homological, like S2 for example, most of them will not admit a polygonal decomposition of this form.
Why not?
Well, because you need like some things should match, right? There is some, like you should be able to kind of decompose your integral affine manifold such that all the singular points lie on the edges of the.
That's fine. I can always add more edges.
But it might, because there's some scattering kind of stuff, they might have to.
No, I'm not I don't think I'm doing any scattering.
It's a condition that's your, you can information.
Yeah, that's what I'm saying. It's a condition. It's not generic. Most of them will.
Certainly, I'm making a lot of restrictions on what I'm doing. We can talk after the talk if you have some objections.
Oh, no, this is great. I'm just.
Yeah, I don't know. I'm restricting myself to very nice cases. That's why I already said, I'm not doing torial crossings, I'm just doing normal crossings. I want these to look like a pair of pants. I'm restricting my discriminant locus to be here. Of course, you can work to generalize a lot of the things. This is just sort of, I'm outlining a program for how you might take smoothing on the B side and recapitulate that smoothing in terms of the Fukaya category. And this is like the simplest case, yeah?
Sorry, I'm a bit confused by what you call D. Is it some sort of divisor compactifying the one-stem manifold?
Yes. Oh, yeah. So, yeah, I never said that. Sorry. Yeah. So D is a divisor compact. D is a. D is something so that x0 union D is equal to X symplectic manifold, which should be mirror to a smoothing of Y0. And the point is, you can kind of check that. So I did this example because I wanted to show that no matter how much singularities I put here, I can put a bunch of x's or do something really weird here. I'm always gluing something into C star squared minus pants, just that the way I'm gluing it in might be sort of complicated. But you can check that I always have it gluing. Like you can compute the sort of symplectic cohomology, or I don't know, compute the sort of contact neighborhood here and see that it matches a contact neighborhood of this thing here. And kind of that's what the nodes are for, is that in order to make sure that that divisor glues into the whole thing and that matches up with the combinatorics of the log structure coming together.
Sorry, another thing that I don't understand is when you say moment X-ray of this divisor, somehow you're assuming that it's a gluing up target pieces as well.
Yeah, well, I just mean that like in this case, this was meant to be kind of imprecise, but I just mean like in this case, you can see it's like on a leg of the pair of pants. Like I'm always kind of on a leg of the pair of pants where it looks like C star to the K degenerating to something. So yeah, I want it to be sort of a degeneration of C star to the K into like something sort of toric, yeah. That's my heuristic. But okay, so what's the idea of computing this deformation? The big idea, so okay, you know, what I want to do is I want to somehow compute this deformation locally. So yeah, Mohammed, I know, has some program to compute deformations locally on the integral affine base. And yeah, I don't understand it, it's very serious. This is something different. It's sort of a cheating way to get what I want in this particular case, which is that use that B-side deformations, right, which are polyvector fields, are étale local on the B side. So what I have is that I know that gluing in this divisor, okay, I should say something about deformations of Fukaya categories. So this is general work of a lot of people, including probably Nick Sheridan is the most important name. There's a sort of, when I have this divisor D, I get a relative Fukaya category, which is a deformation. So I get, there's some category you can define called Fuk XD, which is a deformation of the Fukaya category, maybe the wrapped Fukaya category. I guess in Nick Sheridan's work it's not, it's just the compact Fukaya category, but let me make some assumptions about what the future might look like. Maybe it's a deformation of the wrapped Fukaya category of X0. So what, right, it's a deformation of the wrapped Fukaya category of X0, which is equivalent to coherent sheaves on Y0. And the point is that coherent sheaves on Y0, I have these restriction maps to neighborhoods, coherent sheaves on Y0U. And so sort of, I get a global deformation of this thing, which is a global deformation of this thing. I can restrict it to its various pieces over here. Maybe I should have written this like this, of X0 is equivalent to this, and then of course I have some Viterbo type maps down here to the Fukaya categories of X0U. The point is that this étale locality forces that this deformation is determined by what it does on here, which is what it does on here. The deformation is determined by what it does on local pieces, on local charts. So charts corresponding to charts on this manifold B. And the point is somehow that on these charts, you can see this smoothing class TF. I'll call it TF for now. You can see first order deformation TF, and then you have to check that there are no other curves contributing, that no other curves contribute. So somehow that's you know, my understanding is that it's often difficult to count holomorphic curves, but sometimes it's possible if the number you're trying to count is 0. So we count this one, I know how to do that, and then you sort of need some way to show that the other ones don't contribute. So let me give an example in a local model of what that deformation looks like. And that's going to be the end of my talk, I guess.
So before you raise that picture, can
Yeah.
you draw the monodrom invariant line? Which the monodrom invariant line is transverse to that straight.
Yeah, well, so it must go like this way or this way?
Is that true, or does it go along the edge?
No, it's
It's transverse, right?
It's transverse.
Okay.
I mean, yeah, you know, I mean, locally in this picture, you kind of know what's happening. I mean, if I just did like this part of the picture, then you would know what's happening. This is like, this is the sort of, you can forget about this line. Once I've glued back in the thing, you can forget about this black line. And now what you're seeing is the integral affine base of C2 minus xy equals to 1. right? This is what I get when I glue in this nodal thing in instead of a smooth
And the
thing.
divisor there is just like x equals 0.
Yeah, let me do this example. Let this be my example, and then if I have 1 minute at the end of my talk, I'll write down a Hochschild computation. But, so suppose I start with c star squared minus a pair of pants, 1 plus x plus y. C star squared minus 1 plus x plus y is equal to 0. So I start with that. So that's what I sort of oh, sorry, let me do something simpler here. Sorry. Let me take this picture, which we were just discussing, just one leg of that thing, to be my local model. So here, I see that I have c star squared minus a copy of c star. So minus like x is equal to 1, right? And the point is that what I want to claim is that when I glue back in this divisor, I'm going to get, so I want to glue back in a divisor, and my claim is that what I'm going to get, and this divisor is a nodal thing like this, and my claim is what I'm going to get is c2 minus xy equals to 1. And so how do I get this? So let me look at this c2 minus xy equals to 1. It has a map down to c star by xy. Sort of, it's got one singularity and one missing piece here. And the idea is that if I delete this missing piece here, so if I delete also, say, xy is equal to 0, this is going to be my divisor D. So D is the same in both cases. It's a nodal thing. It's xy equals to 0. Then this base becomes a pair of pants. C star minus 1. So this is now a pair of pants. And also the fiber of this thing is a copy of C star. And I see that what I get is equal to, so this is C star squared. Anyway, you can check that this thing is equal to this thing by a change of coordinates. That's my claim, unless I did something wrong. But that's the.
Which thing? Ideally, if your computation would have worked perfectly.
If my computation was right, and I had practiced this before, then c2 minus xy equals 1 minus this divisor d that I compactified by would be equal to my original thing before I compactified c2 minus x, c star squared minus x equals to 1. So I still believe that's true, but let me just ignore that and have one final minute for a Hochschild cohomology computation. So the Hochschild cohomology, and now C star squared. Okay, maybe I'll just end my talk here, actually, so that I don't confuse anyone further. But you can ask me if you have questions after the talk. So that's it.
If there are no questions, we will see you next week.
Cool.
Thanks again.